and we were able to hear you, just so you know. So if you want to go ahead and bring your stuff up, we'll go ahead and get that going. Well, welcome all this evening to our first in-person public event here at the LPI in almost 3 years. Who was here the last time we had one in December of 2019? Do you remember the topic? It was talking about lunar samples. Well, that's okay. You're here now, and that's all that matters. A little different. Usually they're Thursdays at 7:30. Tonight, obviously, is a little different given what's happening. So thank you all for being here. What's going to happen basically is we're going to hear a presentation from Dr. Edgar Rivera-Valentin about DART mission and about planetary defense in general. Hopefully there'll be some time for Q&A, and at about 10 after 6 at the latest, we will switch back over to the NASA feed, and we'll watch that from there on. So if anybody is at home watching us from home tonight, when we get to that time where we switch back to NASA, I would suggest you to go ahead and just do the same on your own computer, tablet, whatever you're on. Switch over to the NASA feed locally. So right now I want to introduce someone relatively new to the LPI. We have a new director. She started about 2 years ago. Dr. Lewis Proctor went back to APL in Maryland, and Dr. Lisa Gaddis joined us as director from the U.S. Geological Survey Astrogeology branch in Flagstaff, Arizona. And this is her first chance to meet you all.
Hello, hear me? Hi, nice to see you all. So it's my pleasure to introduce Ed. You can see her on the screen. Ed could not be with us tonight. So good evening and welcome to the Cosmic Exploration Series of 2022 speaker series. Ed is at the Johns Hopkins Applied Physics Lab, having started there only about a month ago. Before that, he was at the Lunar and Planetary Institute since 2017. Edgar's educational background includes 2 bachelor's degrees from 2008 in departments of physics and astronomy and Department of Math at Alfred University in Alfred, New York, and a PhD in space and science from the University of Arkansas at Fayetteville. Their research interests including the study of processes that can help inform planetary protection, planetary defense, and planetary exploration. Ed has several major roles in NASA missions. They're co-investigator and planetary defense lead for the OSIRIS-APEX mission, a science investigation team member for the Near-Earth Object Survey mission, or NEO survey, and a sub of the Lunar Reconnaissance Orbiter, or LRO mini-RF radar instrument. The fascinating NASA Double Asteroid Redirection Test, or DART, mission is into asteroid Dimorphos, is the subject of Ed's talk tonight. And Ed, thank you for presenting this evening.
Thank you for the introduction. Saludos, everyone. I'm Ed Rivera-Valentin. As Lisa mentioned, I'm a planetary scientist now at the Johns Hopkins University Applied Physics Lab. APL is actually the institute who built and operated the Double Asteroid Redirection Test mission, or DART, which is the topic of today's discussion. I do have to apologize that I'm not able to be there with you all today. I was really looking forward to chatting about planetary defense and asteroids tonight with you all, but I got really sick this weekend, so I figured I should probably stay away from people for a couple of days to stop spread of whatever the sickness I got. So tonight marks a very monumental event in that we are going to be testing technology that has the ability to quite literally save the entire world from a potential hazard of an asteroid. We are going to be launching the DART spacecraft into Dimorphos, which is a moon of the asteroid Didymos. And then we're going to look to see how that orbit of that mini moon changed over time. If the orbit changed exactly like we predicted, then we have demonstrated that we can change the orbit of an asteroid with this technology, which we call a kinetic impactor. And if it doesn't change it exactly like we predicted it, we're still going to get a lot of data that is going to enhance our ability to then try again. But before we actually go deep into what DART is, we have to take a step back and better understand what planetary defense is. Why do we even care about all of this? So that's what the bulk of the presentation is going to be about, starting to better understand the real hazard, not the Hollywood hazard, but the real hazard of an impact potentially hurting Earth, what that could look like, and why we are developing these type of technologies. So when we look out into the solar system, I mean, if at nighttime, when you look out into the moon, you're going to see a bunch of potholes all over the place, right? Those are craters. They happen when an asteroid or a comet impacts a solid surface at really, really high speeds. It's able to excavate a bunch of material, launches it up into space, and it lands back onto the surface, creating these holes you see in all of these images. But they don't just happen on the moon. When we look across the solar system, we see them everywhere. When we go to Mercury, we see a smiling face crater staring right back at us. That's this crater up here. When we go to Venus, with its very thick atmosphere, impacts are still able to penetrate through that atmosphere, make it to the surface, and create a crater. When we go out into the outer solar system, like the icy moons of Jupiter and Saturn, like Ganymede, which is a moon of Jupiter, and Iapetus, which is a moon of Saturn, we see craters. Craters is that process that just happens everywhere. And sure, many people might not know that this happens on Earth too, but here's a map of impact craters on Earth. It's just on Earth, we have a lot of different geologic processes that can wipe away some of the scars left by impact craters. We have plate tectonics, which quite literally recycle everything. And so it could get rid of a full impact crater. But even then, all of these red dots are impact craters on the Earth. And if you have the chance, there's a really nice example in the US over in Arizona called Meteor Crater. I suggest you visit it. It's really cool to go and look at. And that's a great example of an impact crater right here on Earth. Now, not all impacts form a crater. Sometimes when they're traveling through the atmosphere, they might be small enough that they don't end up reaching the Earth or the ground. Instead, they superheat the air and cause what's called a fireball or fireburst. In this map, what I'm showing you is in color, it's the energy related to those fireball reported events. And this is as recorded by several US government sensors. And you see the range and the amount of energy coming in. And the exact number, it's one of those things where, like, if I said it's 1,000,000 kilometers away, what does 1,000,000 kilometers away really mean? Well, what does log of 2.5 kilojoules means? But this really high red one that you see up there, that's Chelyabinsk. That happened back in 2013. We have videos. You all likely saw this happening. You likely all saw these YouTube videos all over the place of this impact coming through the atmosphere, this really, really bright fireball coming over. And by the way, if you ever start seeing a fireball come down, turn away and don't look at it directly. You could actually cause major retinal damage to your eyes. But when it came down, it didn't cause a crater. Instead, it caused this burst of air as that superheated air finally touched the ground. That broke windows, that damaged buildings. And as you can imagine, those damages also caused hurt to people as glass and other things flew all over the place. There were no casualties reported from this, but there were painful incidences. And this was about 500 kilotons of TNT. So the biggest red one there, that kind of gives you a sense, since we've seen videos of this and we can register what this means. And this one was something on the order of about 20 meters in size, the asteroid impactor. Now, I don't want to make this all about doom and gloom, so let's go back to the statistics and better understand, what is the likelihood of these events happening within our lifetimes? So when we look at really small objects, like a meter or so, we're talking about objects that if they impact they're not going to impact. They're going to just cause like a little burst in the air. These things happen maybe once a year or so. When we move up an order of magnitude up to tens of meters, those are the type of objects that can cause city or town level damage. So that's your Chelyabinsk, right? These we think happen on the order of about once every 1,000 years or so. If we move up another order of magnitude, we're talking about things hundreds of meters. These can cause regional damage. We're talking about potentially the state of Rhode Island getting hit and hurt. These happens once per tens of thousands of years. And for these events, when they occur, the material that gets launched into the atmosphere can later have impact on the Earth's climate. Then when we move up yet another order of magnitude, we're talking about global damage. We're talking about catastrophic level events. And even bigger than these, we're talking about full-on population destruction. And these we think happen maybe once every million years or so. So we think, for example, that one of the reasons that the dinosaurs went extinct was because of something on the order of this size coming down and impacting the Earth, causing a global scale extinction event. But unlike the dinosaurs, we actually have NASA. We have a space program. We can do something about it. And over at NASA, what we do is we have what's called the Planetary Defense Coordination Office. And the person leading this office, I think, has one of the best job titles in NASA, which is the Planetary Defense Officer. Like, who doesn't want to be called that? That's just an awesome name. So one of the things that the Planetary Defense Officer, who's called Lindley Johnson, does is he coordinates all these different aspects that it takes to better understand the severity and the potential or the likelihood of an impact. So the first thing you have to figure out is you have to find these things, right? You have to search them, but it's not just about where is this? Oh, I found you. It's I found you. Let me not lose you. So let me keep track of you over time. And then I need to characterize you. I need to know how big you are. I need to know if you're just a solo asteroid or if you're a binary or trinary system. I need to know your shape. I need to know what your composition is, what your likely density is. I need to know all of these important factors that go into thinking about how do I mitigate this if it becomes a danger to us. And that's actually the next part, which is assess. We found these, we detected them, we tracked them, we characterized them. Now let's assess them. Are they a danger to Earth? What do I need to do? Then I need to plan and coordinate. And now we're at the very important next step finally in mitigate. Because out of all of the natural disasters that can happen on Earth, right? We have Puerto Rico, who just last week experienced a major hurricane, and the state of Florida is about to experience a major hurricane by the end of this week. These are natural events that we can tell people, give them enough warning. Hey, this might happen. We can send evacuation notices. You need to leave because this is going to be a major event. But we can't stop it. To date, we don't have a weather control machine. We can't stop the hurricane. We can stop an impact. Search, detect, track, and characterize, that gets us that Nostradamus ability. That gets us the ability to say, this is going to happen and this is when it's going to happen. But we want to move further than that. And that's the cool part about DART. We're moving beyond just being Nostradamus. We're getting into, let's actually do something about this and stop it and protect the Earth. So now I'm going to go back through these different parts just to give you a little bit more information about these different axes of planetary defense. So let's start off with finding them, right? To find asteroids, as you can imagine, there's a bunch of ground-based telescopes and many astronomers and citizen scientists who spend their nights looking out into the night sky in hopes of seeing a tiny bright dot move across their telescope. And then if they saw something move, they'll report that and they'll look through our catalog and they'll say, okay, never mind, we know this object, but they'll still report what they found because that goes into making sure we keep track of these objects. But if it turns out it's a completely new object, Then we can go and send out an email blast. It's actually through the astronomer's telegram, and it goes out everywhere and everybody gets told, hey, we found a new object. You need to point your telescopes at this. You need to get all the data you can about this. And we put that concerted effort into making sure that we can keep track of this object. Now, if we're only doing this with ground-based telescopes, then we have to wait till nighttime to point the telescope out into space and to see this little bright dot, because if it's daytime, you're not going to see it. And trust me, you also want to avoid looking through a telescope if the sun's out, because that could also cause retinal damage. So this means that we'll be missing out on asteroids that are coming in the direction of the sun. And in fact, that's exactly what Chelyabinsk was. We did not know that that impact event was going to happen because it was coming in the direction of the sun. It wasn't coming from the direction where our telescopes were pointed at. So to overcome this, we have been working on the Near Earth Object Surveyor mission. This is a mission that will hopefully be launched before the end of this decade. And its full purpose is to go out into space and search, track, detect, characterize all of these asteroids, make sure we have a really strong catalog of these potentially hazardous objects, PHOs, to make sure that we now then can move to that step of mitigate. So let's look at the numbers and see how we are in terms of finding all of these objects. So let's go back to that graph I had shown you earlier with the information about each one of the different size and what their frequency was and their potential impact on Earth was. In this case, now I'm showing you 4 meters, 25 meters, 160 meters, 1,000 meters, and 10,000 meters. At the bottom, which is what I want you to concentrate on, is the percent discovered from this population. So these really, really big objects, the 10,000 meters or so, the ones that are mass extinction level events, we're pretty certain we found every single one of those. There are 4 of them that are near Earth objects. We found them all. We're pretty sure. They're big enough. They should be easily spotted. When it comes to 1,000-meter objects, we think we at least have found 95% of those objects. Remember, these will still cause global devastation. So we might be missing 5% of this population. If we look on the other side, the really small side, we maybe know 0.1% of these objects, 0.4-ish. Yeah, these still have a lot of work to be done to find them, but at least these are the type of objects that if they come in, they're causing that bright flash. If they come in, they might cause an airburst, which might cause very small damage to certain buildings, but otherwise should be okay. So the fact that we don't have a good catalog of all of these objects could be okay. The ones that we should be worried about are these 100 or so meter type of objects where we only have 42% of these cataloged. And these can still cause regional, statewide damage. So we're missing a good chunk of these. And that's one of the primary reasons and motivators to have something like the Near Surveyor mission get launched, to finish this up, to make sure that we have our ability to be Nostradamus, should we need that. Now, this was about finding them. There's a next step. Now we have to characterize them. One of the best ways to characterize these type of objects, asteroids, is through the power of radar. With radar, unlike with optical telescopes, you don't just have to sit there and wait for a stray photon from the universe to find its way to your telescope for you to sense it. No, with radar, we can actively transmit light out into space, illuminate the object, and have those echoes come back down to us so we can better understand these objects. So that means that unlike for the optical telescopes, when you see an asteroid, typically it's like a little tiny dot in your image. With radar, we can go all the way up to providing an image, an actual image of this object. We can measure the size of the asteroid. We could see it rotate. We can go all the way down depending on how close and how big this object is. We can go and say, look, there's a crater on that asteroid that's several millions upon millions of kilometers away. That's the power of radar to get us to characterize these objects, which is important if we want to send a mission to mitigate it. The other part that's also important from radar is also from that tracking perspective. So asteroids are typically tens of millions of kilometers away from us. With radar, I can tell you that distance down to a precision of a meter. And asteroids are typically moving at 20 to 60 kilometers per second. I can measure that speed down to centimeters per second. That's the level of precision you want if you want to move from being Nostradamus, being able to predict something that's going to happen a year, 2, 5, 10 years down the road, to being able to predict something that happens 50, 100, 150 years down the road. And we want to provide that long leadway time so that when we send a mission, we don't have to do something super catastrophic to stop the object. We can do like a little nick, and that nick over time grows, and this object can avoid us. So as an example of the power of radar, here's an asteroid radar. Here's a radar image of the asteroid Didymos and its moon Dimorphos. This is a sequence of images. So go from left to right and top to bottom. And that little speck that you see right above the larger half moon, which I'm highlighting now in the magenta box, that's Dimorphos. That's the moon of Didymos. So with the radar, we're literally able to measure the size. I can go from here's the top of the asteroid, measure all the way to the back. And that's how we know that this object is about 780 meters. And we could do the same for Dimorphos and measure its size. And that's how we know it's about 170 meters. We can really precisely know the orbit of this moon around Didymos because we can see it actually move in these images. And with all of this, we could actually put together what's called a shape model, a full 3-dimensional shape model of the asteroid. This one is specifically of Didymos, and you could see little concavities and what might be some craters on it. And this comes from radar and optical images put together. And this is all the type of information, all of the type of information that radar gives us is the type of information you want if you want to do something to defend the Earth. So how do you do this? How do you prevent it? Well, we can totally Bruce Willis this thing and go up and try to explode this with nukes. But one, if you explode it, you still have shards of asteroids heading straight towards you. Two, do you really want to put a nuke on a rocket and send it out into space? That seems like a very dangerous idea. I wouldn't want to do that. So instead of trying to destroy it, which we might have to if we only have like a couple of weeks left, we can just try to change its orbit. And although this image is one of my favorite images about talking about impact prevention, and it looks funny, it's actually real. Like one of the ways that you can change the orbit of an asteroid is by going up and spray painting it. And the change in color from one side to another changes what's called the albedo, so the brightness, and it changes how much light gets reflected off the asteroid. And that amount of light is basically like a little engine that turns on every time it's facing the sun, and it's able to change the orbit of the object. Very slowly, it takes years and years, but it can do it. But this thing about changing the orbit over time, doing a little tiny thing now, but changing the orbit so that in the future, that asteroid and the Earth aren't suddenly found at the same point in space and time, is precisely what we're going to be testing with the DART mission, except instead of spray painting the asteroid, we're doing something called a kinetic impactor, which is a fancy word of saying we're going to take a spaceship and we're going to throw it into Dimorphos and go boom. That's pretty much the mission. So this mission is a huge concerted effort. It's not only NASA, it includes the Italian Space Agency, it includes the European Space Agency, and includes a worldwide net of ground-based facilities who are going to be observing this system after the impact to make sure that the entire process works. So why did we pick Didymos and Dimorphos? Well, first of all, you don't want to test the technology out on just an asteroid, because what if you make it and it moves closer to us? I don't want that. So instead, you find an asteroid that has a moon and you just change the orbit of the moon. We know Didymos has a nice moon called Dimorphos. We have enough data on it that we've seen that period and that rotation, everything about that object going around Didymos really well. We've seen it not change too much over time. So we can pick it and launch DART into it and then wait to see the new orbit. And again, if that new orbit is exactly like we predicted it, then bamf, mission successful, we tested this. If it's not, mission still successful because we're learning a truckload about the strength of these objects and what it takes to actually move it and change its orbit. Now, as you saw in this animation, besides DART, there's also another little CubeSat going along, which is called the SIA Cube. That's part of the Italian Space Agency. So that one was already released. So as DART was coming in, the CubeSat got released and it stayed a little bit further behind. That way, as DART impacts, the CubeSat will then look and see the ejecta that gets launched and gets to capture everything in detail, because obviously once DART hits, we're not going to receive more data. But it doesn't just stop there. About 4 years from now, in 2026, ESA is going to be sending a mission called Hera. The point of Hera is to very, very well characterize Dimorphos. So did we change the shape of it? How big is the crater that we made? How precisely did we change its orbit? We really want to know all of these factors to make sure that we're testing this technology really well. And so this takes more than just one space agency. It takes many space agencies together to really nail down this idea of planetary defense. Now, after my talk, you're going to get to watch the NASA live feed of this event. And in fact, if you missed it, the SIA Cube has a live feed itself. I have it on my iPad on the side, and it's showing you what it's seeing as DART is coming in. But that's going to be preserved online on YouTube, and you can go to it and watch what it was happening. When we're watching this video, you might hear the team use the word beta. What's our beta? So beta is a Greek letter, but besides that, it's when the team is using it, it's using it to encapsulate this idea of momentum transfer. How much energy are we actually transferring into this object? So how much are we actually slowing it down? If we have a low beta, then maybe we're not going to see much ejecta fly off, so much material fly off after the impact. And that means we might not be able to change the orbit by as much as we would have hoped. If we have a middle tier beta, oops, wrong way. We should see some ejecta coming off, and we would then expect big enough change in the orbit. And if this asteroid is a super fluff ball, then we might see a truckload of things flying off of it, and we might be able to change its orbit by a lot. So the story of DART started several years ago. It's pre-pandemic. It's all with the hope of protecting everybody. The mission launched in November 24th, 2021. And then since then, it's been flying to Didymos. And this date was chosen because at this point, Didymos is going to be close enough to Earth that we're going to be able to get really good data from ground-based facilities that are observing the system. And now we're just going to wait to have the spacecraft hit this other object and finally know if we can protect everybody if this thing becomes an actual hazard. That's the cool part about planetary defense. We're protecting the entire world from devastation. And tonight, we're going to finally test these type of technologies. With that, I'll say thank you.
Thank you so much, Ed. Can you hear me all right?
Yep, I can hear you.
And we have about 50 people here who may have questions for you. Ed was planning on being here, but they got sick, so they're not here with us. We're glad all of you are. And let's go ahead and take some questions. I've got some microphones here. If you have a question, raise your hand. Testing. There we go.
Thank you. Now, your background is the Arecibo Observatory, which is unfortunately dead. Now, if we have to characterize asteroid the way you did, and I know you can go all the way to the asteroid belt with a system like that, and in cooperation with the one in West Virginia, the 60-meter antenna, will we have to rely on the Chinese to help us, Nan?
No, so that's a great question. Thank you for asking it. The Chinese FAST telescope is not a radar. It is only a radio. So it does not have the ability to transmit light and to create these type of images. It's much like a regular telescope. It waits for the chance that a stray photon from space is captured in its larger dish. However, we have the Goldstone Solar System radar in California. That is a radar owned by JPL. It is a smaller radar than Asteroid. It is less powerful than Asteroid, but it is able to steer. So it's able to see the entire night sky. And with it, we've been able to continue to study asteroids and track asteroids, get these type of radar images that NASA needs. And then you also mentioned the Green Bank telescope. So Green Bank telescope is also a radio, but in the past couple of years, they've been looking at modifying their system to become a radar to take over the loss of the Arecibo telescope.
What do you do if you get beta 1? Do we just shoot like another test run?
If we get beta 1, or if we get this thing that doesn't move that much, first of all, that tells you a little bit more about the strength of the object. So we think typically asteroids are fluff balls. Some asteroids, you might hear the term monolith. That means a more cohesive rock in space. So if we don't move it by that much, that might be more monolithic than fluffy. We're pretty sure it's fluffy because it's a little moon. But it means that we take all of that data and we better understand, okay, so instead of sending something with this much mass traveling at this much velocity, we need to up that and send more mass with more velocity. And then we go and try again.
So what is the spacecraft doing right now? Is it still accelerating and trying to give us data, or is it basically on rails at this point?
It is on rails at this point. So I didn't mention this during the talk, but besides testing planetary defense technologies like a kinetic impactor, this mission is also testing something called NavCam. NavCam is an automated navigation system that was borrowed from the DoD and is being tested for the first time in planetary science. So after the spacecraft got to a certain distance, NavCam took over. It was able to identify where Didymos is. It then tracked and searched for Dimorphos. It then centered its camera on it, and it keeps changing the thrusters by itself so that it keeps Dimorphos right smack in the middle. And it'll keep taking images through a camera system called Draco up until the point where it smacks into Dimorphos. So we'll be able to receive, in fact, that was one of the things. So after we impact, there'll be about, I think it was 8 or 10 seconds worth of data still coming down. And those will be a lot of those images that the spacecraft took as it pretty much hit.
Hi, what is the mass of the impactor and its relative velocity to the target?
It's a great question. Do I remember the mass of this? It's heavy. You know, this is one of the good things that I'm at home because I can bring up Wikipedia. Let's see here. What is the size of this thing? Ah, here we go.
Dr. Gaddis suggested it might be about the size of a school bus or the mass of a school bus. Is that about right?
610 kilograms or 1,340 pounds.
Heavy.
Much heavier than me.
Yeah. And we've got another one over here.
And the impactor had an ion drive on it, if I remember right. Did that get used and how did it work?
Yep, you're completely correct. So this is testing what's called the next ion thruster system. I don't know much about the ion system itself. I know it's going to be, it is another technology demonstration. A lot of DART is technology demonstration. It's about 3.5 kilowatts worth of energy being excreted. Those are the only numbers I'm remembering right now about it. But it might also be sick brain coming in.
I've got a silly question for you.
Yeah.
Could you say that the CubeSat that's helping is kind of acting like a selfie stick?
Yes. I love that analogy. I should have put that in the slides. A cute little selfie stick. See, a cube is definitely a selfie stick for DART. Now I'm going to put this in my slides. Thank you.
Do we have any other questions? We've got a few minutes remaining before we have to go to the live shot. So.
Oh, yeah. And I'm keeping an eye on the Lucia cube. Oh, it's so cool. So right now, besides having Dimorphos, Didymos nicely centered, it really nicely sees Dimorphos all the sides. So they're now both not point sources. You can see them as separate objects. That is so cool. You can start making out, oh, that's also cool. You can start making out some parts of the shape of Didymos itself. It looks to have, well, I mean, it's not completely spherical. We already kind of knew that. It's a little oblate. It has probably a boulder kind of like Bennu has sticking out on its edge because I see something sticking out. Dimorphos, let's see, let me see if I can like zoom in on those.
We have two more questions for you.
Yeah, go
Ed.
ahead. Go ahead.
Would beta 2 mean that we also would have to shoot out another test launch? Or would we just like say that that's pretty good and just try and strengthen the rocket?
Yep, beta 2 is acceptable. It's pretty good. Things should work enough. Beta 1 is the, oh no, we might really need to consider stuff. Beta 4 is like, wow, this is far weaker than we thought. Beta 2 is kind of Goldilocks zone.
Okay, now if I understand well, you're going to have a spacecraft that's about 700 kilograms at 10 kilometers per second. So that's a nice MV, but let's be realistic. And we have a 10-kilometer bolide coming at us. Would that be realistic to try kinetic impact on something that big that would require a huge mass in space?
Oh yeah, totally. So what was, now that mission's name is going to leave my head. We did something similar when we impacted a comet to look at the ejecta coming back out. Was that deep impact? No.
Was that deep impact or epoxy?
It is deep impact. Okay, I am remembering right. After that event happened, even though that was far smaller in size, far slower, and hitting something ridiculously larger, we were still able to measure a noticeable change in the orbit of that comet. So with something heavier, traveling faster, hitting something that's smaller and far weaker than the comet, we would expect something more dramatic.
Let's go ahead and let's switch our view here so we can see what's being streamed.
Yes.
Ed, you're going to be able to stick with us while we're doing this?
Yes, I might just sit down though.
We absolutely understand that. So, and
with this major milestone and basically all the way up to impact, Lisa Wu, mechanical engineer who helped install the Draco camera and built its.
And we can see in the
bottom.
bottom, there we go.
Last
Awesome.
second comes to pass. So they can do a lot of great up until this point. We just have to see this through to these last few minutes. Well, and in a few minutes, speaking of that, all the years of thinking, of doing, planning, reacting is finally coming to an end. From 5 minutes to impact, there will be no more opportunity to send any commands to SmartNav in the Mission Operations Center. The team will be purely spectators, the data coming in, and they are just wetting it out like the rest of us for the first time. Lori, this is huge, both from an operational perspective and also an emotional one, isn't it?
Yeah, it is. I mean, you can imagine, I'm really excited about it, and I've been engaged with this mission for, the last 4.5 years that I've been in my current role. But this team has been working so hard on this for so many years, and they've put so much of their energy and their time into this, and so much planning and rehearsing. And, it's a really big event for them to, like you say, just counting down and watching. At this point, there's not much else they can do but watch and see the fruits of all their work.
Yeah, I've gotten to know many members of this team over the past few months, and there's a lot of alpha individuals on there, right? You need a good mix of alpha people to make sure we get to this point. I can only imagine. Like you said, a little bit of relief, a little bit of, can I let this go? I have worked for this one so long, and now we can no longer do anything. That moment is just coming up.
Yeah, but I think they're ready. I think they're at that point. You're getting some shots of Elena Adams, the systems engineer, and you can see the excitement in her voice. She's so ready to show the success of this mission.
This is awesome. 5 minutes out, which we're coming up on now. The team will be hands off 2.5 minutes from impact. SmartNav, which has been guiding the spacecraft autonomously for 4 hours, will also step away, stop any maneuvers. DART will simply be coasting to its fate. This is blockbuster stuff, Lori.
Oh, yeah. Oh, yeah. We are there. Yeah.
I have front row tickets, and we are very soon about to open up these airwaves in the Mission Operations Center. We'll stay plugged in all the way through impact. Remember, at this point, 5 minutes out, no more commands to SmartNav will be possible. The team is watching it just like you and me and the rest of us.
So while we're continuing to watch this, if anyone has any further questions for Ed, let us know.
All right, we've reached 5 minutes from impact. The final command opportunity to SmartNav has passed, and the team is simply watching that data stream in just like we are.
Can you tell us which?
Also remember,
to be
there is a
looking
38-second lag for the data to travel to Earth,
do you
and
know
also
which
an additional few
direction
more seconds for image processing.
Can you repeat that one more time?
So when we're looking at it, we have a feel for which direction
The
it'll be
beta would
coming
be in.
You should be hearing.
Yeah. Which part of the
chatter
screen, which
in the
quadrant?
Mission
Any
Operations
ideas?
Center
Does anyone know?
momentarily.
Ed, do you know? Anybody else?
I think
This is DART MSC on DT Mach. 5 minutes till impact. 5 minutes till impact. We are at 1,100 miles away.
okay. I think it's gonna be from the top.
Also, our
If I'm
window
seeing
for
this
sending
right.
any commands to the spacecraft is done. Contingency's done.
It's a great vibe in that Mission
All right.
Operations Center right now, Lori.
It really is. They are so excited. And
This is investigation
I-
one on DT
I'm
Mach.
honing
It's
in,
actually
looking at these
a little bigger
images
than
as we
the
get
CRA.
closer and closer, and you look at Didymos and just, you're starting to see this physical body appear there. It's incredible, just
That sounds
incredible.
great.
I'm
And
still
notice
having a
all the
hard time
craters on
believing this
Didymos.
is
Like I
real
mentioned,
imagery
craters
coming in
are
near
everywhere.
real
It's
time.
also on asteroids. Look at
Yeah.
all those craters.
Yeah, but
Look
you've
at
been
that
watching it over
geology.
the last,
minutes
30,
till
45 minutes
impact.
go from just being a collection of individual pixels, and now the shape and the shading and texture of Didymos. And we're going to see that same thing with Dimorphos as we get closer and closer. This
Is
so
it looking
cool.
like a fluffy asteroid to
Never
you,
before seen
Ted? Can you
images
tell?
of Dimorphos will come into stark relief a few
Absolutely.
seconds before impact.
Didymos.
I mean, they're all
It's
precious
amazing.
and fluffy.
All right.
Excuse me, Ed.
The team is
What's the-
standing just
Two
recognizing
questions.
this
What's the
moment
approach
years
speed
in the making.
and what's the
It is really nice to see
what's the
them
over under on?
relax a little bit, get off
versus
from those computers that they've been glued to, and just appreciate this moment that's coming.
Yeah, and they've earned this. It's just great to see them there.
Were you able to hear that, Ed?
Yes, great question.
Lori,
I
we
don't
hit another
know the
major
numbers off the
milestone.
top of
We
my
are
head.
now
I have to
2
Google
minutes
that.
and a half from impact, and SmartNav has stopped maneuvering the spacecraft. DART is now coasting toward Dimorphos, and we hope into the history books.
Absolutely. This will be, I'm sure you've heard it many times tonight, humanity's first ever attempt at trying to move another celestial body. And also our first attempt ever to execute a mission in sole purpose of planetary defense. So what an exciting time. Yeah, and I'm starting to see Dimorphos start to come into view
Look
there.
at those
You can see it
boulders
starting to take
sticking
shape.
out
I'm
of
starting to see
Didymos.
individual boulders on Didymos. Unbelievable. Unbelievable clarity of images there.
There's a process that that some of our team, Ed, can tell you a little bit about the process that moves boulders up to the tops of asteroids. It's kind of like shaking a box of
All
cereal
eyes on
until the
Savannah
toy comes to
space
the top.
telescopes, ground telescopes from every continent on Earth.
Yeah.
Yeah.
There's some exclamations over that.
2 minutes out. Does not look like one single rock to me.
Oh, boy, we're getting
So
close.
it looks like
14,000
NavCam is
miles
working.
per hour, Lori.
Dimorphos is
14,000
nicely
miles per
centered.
hour. And remember, 45 minutes ago, 55 minutes ago, we couldn't even resolve this object in space. And now you can see us zeroing in right on target.
And we're now dropping the clock, and we'll go by loss of signal to confirm impact.
Right. Yes. Imagine we'll get that loss of signal, and then we'll hear from Lena Adams again, letting us know that
I
we've
feel like
been
we'll know. I feel
successful.
like that'll be a crystal clear signal.
I think so. I think we're starting to see more resolution. In fact, look at that. Didymos has even gone out of the view. We're now just seeing Dimorphos.
This is remarkable stuff.
More of those boulders, right?
Oh my goodness, look at that.
Looks like control system settling down, angular rates look
Yeah,
really
that's
good.
very bouldery
I think we're gonna get the
surface.
investigation team some good pictures.
So this is the NavCam view.
Wow.
I'm trying to pull up the Lucia cube view.
No, come on, we can do better than that.
Starting to see those individual boulders there. You can see shadows of the
Almost
various
30
rocks on the
seconds till
surface.
impact. It's amazing, guys. Oh my goodness, look at that.
Moment of truth.
Unbelievable.
Yeah,
Got rid of the countdown.
looks to me like we're headed straight in.
That's amazing.
Okay, so they said loss
Oh,
of
wow.
signal,
Yeah.
and then a couple more seconds
Oh
more,
my
then they should
goodness.
say everything's
Yeah.
successful.
7,
Oh,
6,
wow.
5, 4, 3, 2,
2, 1.
1.
Okay,
Oh, wow.
now they're celebrating.
Getting visual
It
confirmation.
worked.
It worked. Awesome.
All right.
Woo!
We got it?
Look at those boulders.
Jeez, that's beautiful.
And we have impact. A giant leap for humanity in the name of planetary defense.
Fantastic. Oh, fantastic. Oh,
What a moment. Very few words can really capture this moment. This is beautiful to watch.
Ed, do you have any final words or thoughts for us?
Those images that you just saw will feed at least
Amazing.
dozens of
team.
dissertations
What
in
a
planetary
team, what an
science to come.
Team.
Like, those
2
are
weeks ago, they had their
amazing.
last dress rehearsal. They were getting emotional at
This
the
is
dress
cool. This
rehearsal. They're
is
like,
super
this
cool.
is this is
Y'all
crazy.
just
We're
saw,
getting
like,
emotional. This is not
history in the
real thing.
making.
I can only imagine what they are
Couple
feeling
questions
right
here. The first
now.
one, was it fluffy? Would you say it's
Yes.
fluffy?
With
You
all
can
those
see them
boulders
there
like
on
it
screen.
was,
They're
it's
all
definitely
pretty
looking
excited.
fluffy.
Wow.
Hey, thanks
Hearing
for an
impact,
awesome
the curtains
presentation.
close on
Just,
Draco
I'm wondering
feed.
about the Lucia
Jet Rock
imagery. Is
Joy
that,
from the team.
was that
Years of
streamed
hard work and
live?
the
Is
weight of
there, are we going to be
expectation
waiting
lifted
on
off
those
their
images to
shoulders.
come back?
So Lucia Cube Images had its own YouTube live feed, which I also have way too many screens open right now. But yeah, when you go home, YouTube the Cia Cube DART, and you'll be able to replay everything.
lots more work.
And how
to
do you
happen
spell
with
Lycia if
these
people are
Absolutely. Now,
Googling it?
As I always say, it's one of my
Oh,
favorite
yeah, that's a good
missions.
point.
Now is when the science starts. It just starts now. Now that we've, impacted, now we're going to see for real.
So
how
Lycia.
effective we were. We're going to train all of those ground-based telescopes.
Any other
on the
questions?
Didymos Dimorphos system, and we're going to make measurements that will help us determine just what its orbit looks like now relative to what it was before. So it's going to be great. Very cool.
Very successful
this is when
impact, and we're
science,
glad that you were able.
engineering,
We've got
and
another question here. Hold
a
on.
great purpose, planetary defense come together, and it makes a magical moment.
So
like
there's a
this.
question about, let's see if we can go ahead and get off of the NASA feed and join the Lycia feed.
The team of APL
Grace,
engineers that have really.
we're working
Yeah.
on it. We'll work on
Right
that.
now, the Italians are celebrating
We're
on their
in the
feed.
last words to mark this historic moment.
Oh. We're embarking on a new era of humankind, an era in which we potentially
Okay, so
have the
that
capability.
makes sense. Lycia is
to
an
protect
Italian camera,
ourselves
Dr.
from
Gaddis is
something
saying.
like
So
a dangerous, hazardous asteroid impact.
I wanted
What
to
an amazing
remind
thing.
all
We've
of
never
you
had
that
that
our
capability
next
Thank you,
scheduled
Commissioner.
public
Those are
presentation, our next
last
scheduled
words
public talk
to hear
is in
on.
November. We do
History
have
has
flyers
been
outside. That
made.
one we're planning
to
on
you.
being in person as well. It will be later in the evening, so you don't have to rush home from work to come here.
Day for the DART team.
And we're still working on more details on that, but there are flyers outside for that.
One, asteroids 0. Now I'm here with Nancy Chabot, DART coordination lead. Nancy, talk
Like I
about
said,
a
we'll
moment.
Nancy's awesome. I'm just saying Nancy's awesome.
Your head right now. I mean, I'm just thinking, wow, that was amazing, wasn't it? I mean, those images, you just got closer and closer, and sort of we've been planning for this moment. We've been talking about it for years at APL here. We've been working on this since 2015. And I knew
Ed, in the Lycia feed, were you able to see the extent of how much stuff was distributed, or is that going to come later?
And it really
No, I'm guessing it's going to come later because it was the last few minutes was just everybody excited, and they switched over to the Draco live feed.
And it is just incredible that as humans, like we have done this, we did this. And Nancy, do you have anything you'd like to say?
Having a little bit of trouble finding it right now.
Oh, I mean, I don't need to say anything to the teams because I know everybody like me is really proud to be part of this, right? Proud of this thing that we've been working on for
we've got
years,
a good question here. So is Lycia still out there moving? Is it going to go into orbit? Does it fly past, or does it crash too?
Finally did.
It flies past, so it just keeps going and going and going like the Energizer Bunny.
Investigation team of scientists, telescopes on all 7 continents, everybody doing their part to make this moment happen.
Well, I don't really see the need for us to stay here watching people talking at each other. Does anyone else have any final questions for Dr. Edgar Rivera Valentin?
Can you let us know what's next for this mission?
I want to thank you all for joining us. You are welcome to go hang out, go pick up some materials, go throw some of our magnetic darts at the dartboard. Nobody's going to get hurt. There are no sharp points. And we're so delighted to have you. Please join me one more time in thanking Dr. Edgar Rivera Valentin.
On the team like me are already sending us those images being like, did you see that building? Did you see that street area? Did you see the street?
Thank you.
Oh, I have one last question.
Like taking images and they're storing them, and we'll get those.
Does the shape of the impactor matter?
Yes, 100%. It matters in terms of where you're going to hit it. Yeah, it will matter. If you're hitting a binary asteroid and you just hit it on the edge, it's going to impart a different change in orbit than, or sorry, a contact binary. If you hit it just on the edge, it's going to change how much energy actually goes into changing the orbit.
So
that's one of the reasons we picked this.
The position of it, where it lands on the moon, but the shape of the spacecraft before it.
Oh, the shape of the spacecraft. I'm sorry. I thought you said the shape of the object, like the asteroid.
Yeah, I mean, planetary.
No, at that point, because you're traveling so fast, you're in essence a point source. You're like a little bullet coming in.
No, it doesn't matter. Thank you all so much. We look forward to seeing you again in person soon.
And this idea came
Make sure to
about
ask
from
Beth
animals
questions.
working
She's in the
together
room.
with each other, working together, in order to make this
And if
moment
anyone
happen
has
for
any
NASA
further
scientists.
questions,
Coordination
Betseda
office,
Aponte
building the
Hernandez
spacecraft
here is
at
also happy to
APL.
answer some
But
questions.
really, scientists around the world are ready to get studied. What did we do to Dimorphos? But more importantly, what does that mean for potentially applying this in the future? I mean, DART really is just the start. It's just the first planetary defense
My
test
team did
mission.
all the work.
It was spectacular
My team
and it's
did all the
accomplished
work.
and we'll
It's just-
figure